Hi, welcome back to our class in Differential Calculus or Calculus 1. In Lesson 1, we took up the meaning of derivative of a function at a specific value of the independent variable. In Lesson 2, we introduced the concept of limit of a function. And for those of you who missed these first two lessons in differential calculus, please search for my videos. Art teaches Calculus 1, Differential Calculus, Lesson 1, the meaning of derivative, and Art teaches Calculus 1, Differential Calculus, Lesson 2, limit of function. In Lesson 2, we said that the limit of a function exists if the right-hand limit and the left-hand limit of the function are equal, numerically equal. And we now state that as a theorem. Again, we let y equals f of x as our function. We write our findings last time as a theorem. This is one of the limit theorems. And the limit theorems are what we will apply when we evaluate the limits of functions. When evaluating the limits of function, we will be guided by what is known as limit theorem. Let our function be denoted by y equals f of x. Then, the limit of f of x as x approaches a equals L if and only if limit of f of x as x approaches a from the left equals limit of f of x as x approaches a from the right. And these limits from the left of f of x and this limit of f of x from the right are both equal to L. This theorem is an example of a biconditional statement or an if and only if statement, as you may have studied in mathematical logic. The first part of the biconditional statement, the first part of this biconditional statement is that if the limit of the function f of x as x approaches a is equal to L, then the limit of f of x as x approaches a from the left is L. The limit of f of x as x approaches a from the right also exists and it is equal to L. And both the left-hand limit and the right-hand limit of f of x are equal to L. The second part of this if and only if statement is that if the limit of f of x as x approaches a from the left, that is the left-hand limit, and the limit of f of x as x approaches a from the right, that is the right-hand limit, if the left-hand limit of f of x and the right-hand limit of f of x are both equal to L, then we can conclude that the limit of the function f of x as x approaches a is equal to L. We will now take an example to show that the right-hand limit and the left-hand limit of a function, if they exist, is equal to the limit of the given function. We will now apply the first theorem that we had earlier. Consider the following example. We let the function f of x be equal to 3x plus 1 if the values of x are less than 1. If the values of x are greater than or equal to 1, then the value of the function is given by 5 minus x squared. We will find the limit of the function f of x as x approaches 1. For this example, we will find the left-hand limit, that is the limit of f of x. The limit of f of x as x approaches 1 from the left. And we will also find the right-hand limit. The right-hand limit is given by limit of f of x as x approaches 1 from the right, indicated by positive sign or plus sign. And if we find that the left-hand limit is equal to the right-hand limit, and we can conclude by the theorem that the limit of f of x as x approaches 1 is equal to that value of the left-hand limit and the right-hand limit. And we use this method only when the given function has 2 or more values depending on the value of the independent variable. For the left-hand limit, the limit of f of x as x approaches 1 from the left, this means that the values of the independent variable x are approaching positive 1 from the left, or the values of x are those numbers that are less than 1. And for the values of x that are less than 1, the function value is given by 3x plus 1. And we substitute 3x plus 1 into this to find the limit of f of x as x approaches 1 from the left. For the right-hand limit, or the limit of f of x as x approaches 1 from the right, this means that the values of x are approaching positive 1 from the right, or the values of x are numbers that are to the right or greater than positive 1. If the values of x are greater than positive 1, then the value of the function is given by 5 minus x squared. Thus, we will use f of x equals 5 minus x squared to evaluate the right-hand limit of the function. We replace f of x with 5 minus x squared, and we evaluate the limit as x approaches 1 from the right. By evaluating the limit of f of x as x approaches 1 from the left, in this limit, the values of x are less than 1. And the value of the function when x is less than 1 is given by 3x plus 1. So in this limit, we replace f of x with 3x plus 1. And we get limit of 3x plus 1 as x approaches 1 from the left. As x approaches 1 from the left. We have not taken the other limit theorems, but if you are evaluating the limit of a polynomial function, it is similar to evaluating that polynomial function at a specific value of x. For instance, in this example, x approaches 1, we simply substitute 1 for x in this function 3x plus 1. Replace x with 1, and we get limit, simply replace x with 1, and we get 3 multiplied by 1 plus 1 equals 3 by 1 is 3 plus 1 is 4. Later on, we will state the theorem about evaluating a polynomial function. Again, when you are getting the limit of a polynomial function as x approaches a specific number, simply evaluate the polynomial function at that specific number. Like limit of 3x plus 1 as x approaches 1, we simply replace x with 1 and we get 3. 3 multiplied by x is replaced by 1, multiplied by 1, plus the constant 1, which gives us 4. Now we find the right-hand limit of the same function. We write limit of f of x as x approaches 1 from the right. In this limit, the values of x are greater than positive 1, or the values of x are those real numbers to the right of 1. When the value of x is greater than 1, the value of the function f of x is given by 5 minus x squared. Hence, in this limit, we replace f of x with 5 minus x squared, because the values of x are approaching 1 from the right, which means that the values of x are greater than 1. And we have limit. For f of x, we use 5 minus x squared. Because as we said, the values of x are greater than 1. When x is greater than 1, the value of the function is 5 minus x squared. And we evaluate the limit of this function as x approaches 1 from the right. Again, when evaluating a polynomial function, evaluating the limit of a polynomial function, we simply evaluate that polynomial function at a specific value of x. As in this example, this is a polynomial function. In particular, it is a quadratic function. And we find the limit of this quadratic function as x approaches 1 from the right. And to evaluate this limit, just replace x with positive 1, or substitute positive 1 for x. And we get 5 minus, replace x with 1, 1 to the power 2. And we get 5. The square of 1 is 1. 5 minus 1 is 4. Hence, the right-hand limit of f of x as x approaches 1 from the right is 4. And 4 is also the left-hand limit of the function f of x, or the limit of f of x as x approaches 1 from the left. Therefore, by the theorem the first theorem we had earlier, we can conclude that the limit of the function f of x as x approaches 1, we now omit the plus and minus sign here. We simply write limit of f of x as x approaches 1 is 4. And 4 is the left-hand limit of the function, and 4 is also equal to the right-hand limit of the function. We will now sketch the graph of this function to see what this limit of 4 means graphically. And in sketching the graph of the function f of x, the skills that you learn in analytic geometry will be very useful. We now sketch the graph of the given function f of x, which has two values. F of x equals 3x plus 1 if x is less than 1. And the value of f of x is 5 minus x squared if x is greater than or equal to 1. And we have shown that the limit of the function f of x as x approaches 1 exists. In particular, the limit of the function f of x as x approaches 1, we have shown is equal to 4. Because the left-hand limit and the right-hand limit of this function exist, and both of them are equal to 4. Now we will sketch the graph of this function f of x in the Partition Plane that consists of two axes. In the vertical axis, we write y, the dependent variable y. In the horizontal axis, we write the independent variable x. The horizontal axis is denoted by x. And at the intersection of the two axes, this point is indicated by 0 or the origin with coordinates 0, 0. You can see that in the horizontal axis, I use a 1 unit intervals. In the vertical axis, I also use 1 unit intervals, although the length of 1 unit in the vertical is not the same as the length of 1 unit in the horizontal. But that is okay as long as you indicate the interval that you use in both axes. That's why it's very important that you label the y and the vertical axis with the interval that you use. Again, in the horizontal axis, I use a 1 unit intervals. In the vertical axis, I also use a 1 unit intervals. But you may use other intervals for the two axes. You may use a 2 unit intervals in the horizontal axis. So you will start from 0, 2, 4, 6, etc. You may also use a 2 unit intervals in the vertical axis. So you will start from 0 and then you count by 2. 0, 2, 4, 6, 8, etc. We start with the graph of the first value of the function 3x plus 1 when x is less than 1. Generally, we denote a function using this notation y equals f of x. And when x is less than 1, the value of the function is 3x plus 1. So we replace f of x with 3x plus 1. And the value of y, the dependent variable, equals 3x plus 1 for value of x less than 1. Since this is a linear equation, linear in two variables x and y, we know from analytic geometry that the graph of this linear equation or linear function, linear in two variables x and y, is a straight line. And the graph of this linear equation is neither a vertical line nor a horizontal line, which means that the line, the graph of this linear equation will have a y-intercept and an x-intercept. That means the line, the graph of this linear equation will intersect both the x-axis and the vertical axis. And we will find the intercepts of the line, which is the graph of this linear equation. We start with the x-intercept or the point on the x-axis through which the line will pass. The x-intercept is a point on the x-axis, and any point in the x-axis, the value of y equals 0. So to find the x-intercept, you set y to 0. When y equals 0, you substitute 0 for y and you solve for x. When y equals 0, the left side is 0, equals 3x plus 1. And transpose to solve for x, you transpose positive 1 to the other side of the equation. And from the other side, 3x will be left on the other side of the equation. We have 3x. 3x equals, transpose positive 1 to the left, we get negative 1. And to solve for x, we divide the left side and the right hand side of the equation by 3. And constant 3 will cancel out from the left. And we get x equals negative 1/3. Or the x-intercept, the intersection of the line and the x-axis is a point with coordinates. Abscissa is negative 1/3. And the ordinate is 0. If you plot this point, negative 1/3, 0, it is a point on the x-axis. Specifically, this point is a point to the left of the vertical axis. And we plot this point, negative count 1/3 unit from the origin. This is the origin. And you mark 1/3 in the horizontal axis. This is the point negative 1/3 and 0. This is known as the x-intercept of the line, the graph of this linear equation y equals 3x plus 1. When we draw the line should pass through this point on the x-axis. Now we find the intersection of the vertical axis and the line, the graph of y equals 3x plus 1. The y-intercept is a point on the y-axis. And any point on the y-axis has a value of 0 for the abscissa, or the variable x. So to find the y-intercept of the line, or the intersection of the line with the vertical axis, you set x to 0. When x equals 0, replace x with 0 in this linear equation. From the left, we get y equals 3 multiplied by 0 plus 1. And y is equal to 3 by 0 is 0 plus 1 is 1. And we write the y-intercept, the intersection of the line and the vertical axis. The y-intercept is at the point 0 and 1. If you plot this point, you will know that this point is a point above the horizontal axis. We plot this point. X is 0 and y is 1. And that point is this point with coordinates 0 and 1. X is 0 and y is 1. The line will pass through this point on the vertical axis, and it is called the y-intercept of the line. To construct the line with equation y equals 3x plus 1, just connect the two intercepts, the x-intercept and the y-intercept, with a straight line. So we do that, connect the two intercepts with a straight line. This is the graph of f of x equals 3x plus 1, or y equals 3x plus 1. And we label this line with its equation y equals 3x plus 1. We next graph the function f of x equals 5 minus x squared for values of x that are greater than 1. And in this function notation, we now replace f of x with 5 minus x squared. That's the value of y when x is greater than or equal to 1. In our notation for function y equals f of x, the value of f of x now is 5 minus x squared for values of x that are greater than or equal to 1. So we write y equals 5 minus x squared when x is greater than equal to 1. We will now sketch the graph of this equation y equals 5 minus x squared. And you can see from this equation that this equation is quadratic equation in the variable x. And we know from analytic geometry that the graph of quadratic equation, quadratic in either x or in y, is a parabola. And this is a quadratic equation in x, and the graph of this quadratic equation is a parabola, whose general equation is of the form y minus k equals 4p times quantity x minus h to the power 2. This is the general form of a quadratic equation in variable x. And we should write this equation y equals 5 minus x squared in this form for us to find the vertex of the parabola and to find whether the parabola opens upward or downward. When the quadratic equation is linear in y, the parabola is either open upward or open downward. When the quadratic equation is linear in x, the parabola is either open to the right or open to the left. In this example, our quadratic equation is linear in y. Hence, the parabola is either upward or open downward. And the value of 4p will tell you whether the parabola is open upward or downward. If 4p is positive, greater than 1, greater than 0, then the parabola is open upward. If the value of 4p is negative, then the parabola is open downward. Now we write this equation in this form for us to find the vertex and for us to know whether the parabola is open upward or downward. All the constants should be transposed to the left side. So we start by transposing 5 to the left side. And we get y minus 5 equals negative x squared. Comparing this general form of quadratic equation in x, we now can see that k is equal to 5. But we cannot tell yet the value of h. But we can find the value of h by rewriting x as x minus 0. X equals x minus 0. We have y minus 5 equals negative. Open parenthesis, we write x now as x minus 0 to the power 2. Now you can see that if you compare this equation in this general form of quadratic equation in x, you can see that h is equal to 0. And the coefficient of this square of x minus 0 is negative, which means that the coefficient of this square of x minus 0 is negative 1. And negative 1 is the value of 4p. We write 4p equals negative 1. 4p is the coefficient of this quantity, square of x minus h. And the coefficient of our quantity, square of x minus 0, is negative 1. Hence, for p equals -1, and -1 is less than 0. Therefore, the parabola, the graph of this quadratic equation in x is a parabola that opens downward. Now we find the vertex of the parabola. The vertex of a parabola is denoted by the point HK. And our H is 0. And our K is 5. So this is the vertex of the parabola, the graph of this quadratic equation in x. And since the parabola is open downward, this vertex is the highest point on the parabola. And if you plot this point is a point on the vertical axis. 5. This point has coordinates 0, 5. And this is the vertex of the parabola. It is the highest point on the parabola. And the parabola will open from this point downward. If the parabola opens downward, the parabola will intersect the horizontal axis or the x-axis. The points of intersection of the parabola with the horizontal axis are the intercepts of the parabola. And we will now find the intercepts of the parabola. The intercepts of the parabola or the intersection of the parabola with the horizontal axis are points on the x-axis. And we said earlier that any point on the horizontal axis or x-axis, the value of y equals 0. Thus, to find the intercepts of the parabola or the intersection of the parabola with the x-axis, we set y to 0 in the equation of the parabola. So we set y to 0, y equals 0, equals 5 minus x squared. We get this equation when y equals 0. And we set y to 0 because we want to find the intercepts of the parabola on the x-axis. From this equation, you can readily solve for the value of x by transposing negative x squared to the left side. We get x squared equals 5. And you take the root of both sides, and the values of x are plus and minus. X has two values, the positive root and the negative root of 5. And the root of 5 to 2 decimal places is approximately equal to 2.24. So the parabola will pass through the x-axis at 2.24 and at negative 2.24. We approximate 2.24. This is 2 units. Suppose this is 2.24. 2.24. From this vertex of the parabola will go downward, and it will pass through this point on the x-axis. The other x-intercept is negative 2.24. We approximate negative 2.24. This point is negative 2. And this is our negative 2.24. From this vertex of the parabola will go downward, and it will pass through this point on the x-axis, negative 2.24. Notice that if the parabola goes down from this vertex, it will intersect this point 2.24 on the positive side of the x-axis. But the parabola will also intersect the line, whose equation is y equals 3x plus 1. So before we sketch the parabola, we know that the parabola has a vertex at this point. We know that the parabola will go downward and will intersect this point and this point on the x-axis. We first find the point of intersection of the parabola and this line, whose equation is y equals 3x plus 1. And the equation of the parabola is y equals 5 minus x squared. And to find the point of intersection of the parabola and the line, we solve the equation of the line and the equation of the parabola simultaneously by using a method which you have learned from your algebra.
Maybe then you'd still be a part of me. I was wrong not to let you know this feeling that's hard for me to show. Since you've gone, I've always been alone, feeling down and sorry for myself. I look at your picture and there I find I won't make it through another rain without your sunshine. I need you back, I need you here to guide me. Please come back, you're the only one who's ever loved me. I need you back, let's start all over again. Share the love you have for me then. Since I've said what I came here to say, yes, I'd have me going on my way. But before I go, I just gotta let you know you're the only one who can make me happy again. I need you back, I need you here to guide me. Please come back, you're the only one who's ever loved me. I need you back, let's start all over again. Share the love you have for me then. Share the love you have for me then.
We now solve the equation of the line y equals 3x plus 1 and the equation of the parabola y equals 5 minus x squared simultaneously. Since both of them the right-hand sides of these equations are equal to y, we simply equate 3x plus 1 to 5 minus x squared. We have 3x plus 1 equals 5 minus x squared. And the reason we are solving this linear equation and quadratic equation simultaneously is because we would like to find the point of intersection of the parabola and this straight line. And to solve for that point, for the coordinates of the point of intersection of the parabola and the line, we have to solve the equation of the line and the equation of the parabola simultaneously. And what we did here is we equate 3x plus 1 with 5 minus x squared, since both of them are equal to y. And from this equation, we solve for x. And after we solve for x, we solve for the value of y. Transpose negative x squared to the left-hand side of the equation, it becomes positive x squared plus 3x plus 1. Transpose 5 to the left, it becomes negative 5 equals 0. And we simplify the left-hand side of this equation. We have x squared plus 3x. And 1 minus 5 is negative 4. This equation is a quadratic equation in x. And for solving a quadratic equation, you can use any one of the methods for solving quadratic equation, including factoring, quadratic formula, completing the square, or any other method for solving quadratic equation. But the simplest way is to use the method of factoring if the quadratic expression is factorable. But this quadratic expression x squared plus 3x minus 4 is factorable. And for factoring, you may use trial and error. The factors of x squared are x and x. So you start by factoring the first term. The first term is x squared, and the factors of x squared are x and x. And then factor out the constant term, and negative 4 has many possible factors. One is negative 4 multiplied by 1, positive 1. The other is positive 1 multiplied by... Negative 4 has many possible factors. One set of factors for negative 4 are negative 4 and positive 1. And another set of factors for negative 4 are positive 4 and negative 1. So you can choose negative 4. You write as the product of negative 4 and positive 1. Other possible factors for negative 4 are positive 4, positive 4, and negative 1. So negative 4 can be factored as negative 4 and times 1, positive 1. Or negative 4 can be factored as the product of positive 4 and negative 1. Negative 4 multiplied by positive 1 is negative 4. Positive 4 multiplied by negative 1 equals negative 4. But we want those factors that will give us a sum of positive 3 in the middle term. So you check which of these factors will give a sum of positive 3, coefficient of the middle term, if you add these factors of negative 4. For the first set of factors for negative 4, we have negative 4 and 1. If you add negative 4 plus negative 4 and 1. If you add negative 4 and 1, or negative 4 plus 1, you get negative 3. But negative 3 is not the coefficient of the middle term. The coefficient of the middle term is positive 3. So we check the second set of factors for negative 4. We have positive 4 and negative 1. If you add positive 4 to negative 1, or positive 4 plus negative of 1, you get positive 3. Therefore we take these factors of negative 4. And we write it here. The first factor of this quadratic expression is x plus 4. And the other factor of this quadratic expression is x minus 1. To solve for x, you now equate each linear factor to 0 and solve for x. And we do that for the first factor, x plus 4. X plus 4 equals setting to 0. And from this linear equation in x, we get x equals, transpose positive 4 to the right, we get negative 4. And we do the same for the second factor of this quadratic expression, x minus 1. X minus 1 equate to 0. And you get x equals, transpose negative 1 to the right, you get 1. Positive 1. So the roots of this quadratic equation, x squared plus 3x minus 4 equals 0, are x equals negative 4 and x equals positive 1. Which means that there are 2 points of intersection of the parabola and the line. One point of intersection is at the right of the y-axis, and the other point of intersection is at the left side of the y-axis. And this quadratic equation has 2 roots because a quadratic equation has an equation quadratic in variable x has always 2 roots. The exponent of x, the highest exponent of x2 indicates that this equation has 2 roots. And for each value of x, we will now solve for the value of y using this equation, the linear equation, or using this quadratic equation. We now find the value of y when x equals negative 4 and when x equals 1. You substitute the value of x using this linear equation or using this quadratic equation. It is easier to use this linear equation. Substitute the value of x and solve for y. We start with x equals negative 4. Using the linear equation, y equals 3 multiplied by the value of x. X is negative 4, the first solution of the quadratic equation we solved earlier. 3 multiplied by negative 4 plus 1. And y equals 3 by negative 4 is negative 12 plus 1. And negative 12 plus 1 gives us y equals negative 11. So the first point of intersection of the parabola and this line is the point with coordinates negative 4 and negative 11. This point is a point in the third quadrant where x is negative 4 and y will be way down below at negative 11. Now we solve for the value of y using this linear equation when x equals 1. We get y equals 3 multiplied by x1 plus 1. And y equals 3 by 1 is 3 plus 1, 4. Hence, the coordinates of the other point of intersection of the parabola and the x-axis is the point with coordinates 1, excuse me, and y is 4. And this point lies in the first quadrant where x is 1 and y is 4. We will now complete the graph of our given function. Now complete the graph of the function f of x. Initially, we have drawn the line with equation y equals 3x plus 1. This is the intercept of the line with coordinates negative 1/3 and 0. And this point with coordinates, this point on the y-axis with coordinates 0 and 1 is the y-intercept of the line. And we draw the line passing through these points or intercepts. And we obtain this line with equation y equals 3x plus 1. We also know that the vertex of the parabola is at this point on the y-axis with coordinates 0, 5. And we also know that from the vertex is the highest point on the parabola. So from the vertex, the parabola will go downward. And the parabola will intersect the x-axis at this point, positive 2.24. And the parabola will also intersect at this point on the x-axis at negative 2.24. We solve the equation of the line and the equation of the parabola simultaneously to get the points of intersection of the parabola and this straight line. And we obtain these coordinates of the points of intersection of the line and the parabola that we will now draw. The first point of intersection is the point 1, 4. X is 1 and y is 4. This is the first point of intersection of the line and the parabola, the point 1, 4. When you draw the parabola that opens downward from the vertex, the parabola will go downward. It will pass through this point on the line because this is the point of intersection of the line and the parabola. And the parabola will go downward. It will pass through the x-axis at positive 2.24. We draw that part of the parabola. From the vertex of the parabola opens downward. It will pass through this point on the line because this is the point of intersection of the line and the parabola. And from this point, the parabola will continue to go downward. It will pass through this point on the x-axis, x equals 2.24. This is the intercept of the parabola. To the left of the y-axis, we also draw the part of the parabola to the left of the y-axis. From the vertex, the parabola will go downward. It will intersect the x-axis at this point, x equals negative 2.24. This is also the x-intercept of the parabola. So we draw this part of the parabola to the left of the y-axis. From the vertex, the parabola will go downward, passing through this point on the x-axis at x equals negative 2.24. And from this point on the x-axis, the parabola will continue to go downward. If it goes downward, it will intersect the line again with equation y equals 3x plus 1. And the second point of intersection of the line and the parabola has coordinates negative 4, negative 11. So from this point, the parabola continues to go downward, and it will intersect the line. This is the point of intersection of the line, and this point of intersection of the line and the parabola has coordinates -4 and -11. -4 and -11. Where x is -4 and the value of y is -11. The values of y below the x-axis is -11. So this is the graph of the line and the parabola. We label the equation of the parabola. The equation of the parabola is y equals 5 minus x squared. You can see that there is an area bounded by the parabola and the straight line. In integral calculus, one of the problems in integral calculus is finding the area bounded by two curves. In this example, the area bounded by this part of the parabola and this part of the straight line. And you can find this area using the process of integration, but we will not do that because our course is differential calculus. Now, this is not the entire graph of the function f of x, which means that not all of these constitute the graph of the function f of x. We only show for the graph of the function f of x, we only show the part of the line with the equation y equals 3x plus 1 for those values of x less than 1. And we remove the part of the line where the values of x are greater than equal to 1. We are interested only with the part of the line where x is less than 1. And this is x equals 1. When x is 1, the value of y is 4. And we retain the part of the line for values of x less than 1. For values of x less than 1, that's from positive 1 and all the numbers to the left, the graph of the function will start from this point down to the left. And this point is not actually included on the line because it says in the given function x is less than 1. So x is not equal to 1 for the function 3x plus 1. So from the graph of this linear equation y equals 3x plus 1, we remove this part of the line because this part of the line, the values of x are greater than 1. We do the same for the graph of the parabola with equation y equals 5 minus x squared. We retain the part of the parabola with equation 5 minus x squared for those values of x greater than equal to 1. And we remove the part of the parabola where x is not greater than equal to 1. That is, x is less than 1. And this is x is 1. For this value of the function 5 minus x squared, x can be equal to 1. And when x is 1, you can see that the value of the function is 5 minus 1 squared is 4. When x is 1, the value of the function is 4. And that's exactly the point of intersection of the line and the parabola. The function has a value when x equals 1. And the value of the function is 4. So this point, 1, 4, is a point on the parabola. It is included in the graph of the function f of x. But for x less than 1, this is 1. The numbers less than 1 are the numbers to the left of 1. And for those values of x less than 1, we remove this part of the parabola. It is not part of the graph of the function for x less than 1. For x less than 1, the graph of the function is that part of the line with equation 3x plus 1 when x is less than 1. So for x less than 1, we remove this part of the graph of the parabola. And the remaining part of the line and the remaining part of the parabola constitute the graph of the function f of x. This is the complete graph of the function f of x when x is less than 1. From this point, you have this straight line, the graph of f of x. For x is greater than equal to 1, from positive 1, this is the graph of the function f of x. This is a part of the parabola. And this is the graph of the function f of x. We have shown that the limit of the function f of x as x approaches 1 is 4. So when the value of x approaches 1, either from the right of 1 or from the left of 1, the value of the function approaches 4. Again, when x approaches 1 from the right or when x approaches 1 from the left, the value of the value of the function approaches 4. So 4 is the limit of the function if x approaches 1. Today we learn how to evaluate or find the limit of a function if the function has two values, or if the function is defined by two function values depending on the restrictions on the values of the independent variable. When the function is defined by two function values depending on the restrictions imposed on the independent variable, you take the left-hand limit, get the right-hand limit, and if the left-hand limit is equal to the right-hand limit, then you conclude that the limit of the function exists. And that is our first theorem. And in the next lesson, we will take more limit theorems that are useful for evaluating the limits of functions. If you have questions about the lesson today, don't forget to write your comments below and ask your question. And also don't forget to subscribe to my YouTube channel, Art Kalisan. And thank you for joining me in our class today.